Okay, so just do a very quick recap of what we saw the last time. Last time we did look at data structures, and we said they are simply a way to organize data based on the need you have, right? But again, I don't know if everybody that's here were in the last time. So very quick intro. My name is Charles. Jerry might have introduced me already. So Charles will introduce my name. And I'm Nigerian, of course, background computer engineering, currently tech lead for a fintech / wealth tech company in North America, just like RiseVest, but like really big. And tech lead for our largest clients right now. Some fun facts: been around in tech for a very long time. I played the bass. I used to be in a music group. I used to sing a lot back then, but I don't know. I guess I can find my way back to that. Published my Java title back in 2012. Done a number of things here and there. Was very involved in the community in Nigeria before I left. Still involved. Was at Google. Was at Andela. You can check me out on LinkedIn or Twitter or whatever. Yeah. And so I was saying that the reason why we invest time to, build the knowledge and the skill of data structures and algorithms, because people argue and say it's not valuable. I've seen conversations on Twitter, on YouTube saying, you spend 5 years or 10 years in your career as a software engineer and you never have to write your own algorithm. You never have to build your own data structure. So there's some elements of truth there, but that's not the whole truth. It's not absolutely true, right? And so, for example, I have had to come up with my own data structure, and I have had to use an existing algorithm, but know how and when to use it. Okay, and I've had to write my own small, simple algorithm. And I'm saying small, simple, not to diminish the value, but to say, it's not published in a tech journal. It's not like in an academic publication, like the algorithms that we have, that we know and learn in computer science. But knowing and understanding data structures and algorithms actually gives you a superpower. And I'll just breeze through what we went through the last time to say the reason for that. The way I like to phrase it is that you are in a constant battle as a software engineer, and the battle that you're fighting is, in a constant battle, you need to be battle ready. And the battle you are fighting is the battle of how do I go from problem to solution. Like, you're constantly solving problems. Like, even as a tech lead today, I'm responsible for solution architecture, all those high level things, but I'm also very hands-on. I'm also writing code. Okay, so every sprint I have either very critical bugs to fix or very critical end-to-end solutions to either design or build, And so some of those problems, they come in as very vague things that the customer wants, or that even, we distill what the customer wants, but how do we go from that to an actual solution? Even if the problem is well designed, well defined, sometimes going from problem to solution, it's a long journey. So that's something that you're constantly doing as an engineer. It's easy to think that, right now you might be thinking, I want to put validation in this field, or I want to, you can be thinking in those micro contexts, but as you go further in your career, you would see that that's just a microcosm of the kind of problems you'll be solving. And so that constant problem to solution is a battle, and you need to be able to go from that correctly, efficiently, effectively, and also quickly. And one of the superpowers that allows you to do that is pattern matching. Pattern matching, I'm just breezing through because we covered this the last time. Pattern matching is a journey, but it's actually a number of things. It can be, because I have very solid computer science fundamentals, I went to a very good school, I did a very good course online, it gives you that ability to pattern match or problem solve. Or, I'm very hands-on, you've been very hands-on, that might be your case, even if not now, maybe a couple of years to come. And then because of all that experience, you're able to pattern match, you're able to, go from problem to solution. But another way, which is I highlighted here, is data structures and algorithms. That knowledge, even if you're not writing your own data structure or your own algorithm, that ability just equips you to quickly pattern match. It builds your your thinking ability, it builds your intuition and your problem solving skills. And another thing I'm trying to highlight here with this slide is that there are two big things that software engineers need to, big skills that software engineers need to have: problem solving and communication. In my opinion, and this is not just opinion based on personal, like what I feel, is based on data, based on like what I've seen. The number one, I need to update this slide. The number one skill that software engineers need to have is actually communication. It's not like writing code. So junior engineers, intermediate, even some senior engineers think writing code, writing the best code or the best infrastructure, or the best whatever, the tech hard skills is what they really need. But the soft skill, the communication is the biggest skill. So I can tell you for a fact that I don't want to digress, but for example, in my current role, maybe this might actually help to drive the home point. In my current role, I actually interviewed for a senior software engineer role. Right, so that was what was advertised. That was what my first interview was. But after I met the hiring manager, who was a director of software engineering, she was a former CTO. Like, she's very grounded. After I met her, she was like, "Oh no, this guy is senior software engineer is small for this guy. Like this guy is way higher." And when I asked her later, she said one of the things that made me stand out was how I spoke. And how I spoke is not necessarily just throwing fluffy words around. It's how I was able to like distill the technical challenges that she gave me, like, take it, phrase it in my own words, break it down, define a scope, itemize them. Like, I don't want to go into all of that, but the point I'm trying to make is that's just an example to say it's okay to have the hard skills. Not it's okay, it's good, it's great to have the hard skills, software engineering, system design. Like, you can build the best React component, you can build the best API backend, whatever, But I've seen, and I've both in my own personal career and people around me, that the engineers who are able to do a great job talking to customers, talking to clients, talking to product people, talking to very senior leadership, and talking to, I don't mean like literally talking to, I mean like whether it's written, whether you're in meetings, whether you are able to communicate your goals, like that whole thing. Those engineers, they go very far. Either in terms of they are very effective, either in terms of they get quick buy-in from their things that they want to do. People gravitate toward them, they get promoted, like that whole stuff, So communication is like the number one skill if you want to like be very successful. But the number two, when it comes to like your hard skills, there's a problem in front of you that's technical that you need to solve. Data structures and algorithms is one way that enables you to like, improve how you think, improve how you process information, improve how you structure that information, how you approach the problem, and how you go to solution. Okay. And so for last week, part one, we looked at data structures. We said there are just a simple way of organizing your data, organizing it, knowing that you are doing that with a goal in mind, right? And we look at this example. The goal is safekeeping and easy access. How do you organize books and fruits? If I give you a large bag, okay, of books and fruits. And we looked at how it makes sense to put the books on a shelf because you want to easily access them. You want to be able to see their titles, and the fruits, you might put them on a tray, on a bowl or something. And we looked at arrays. We said arrays are just a way to store things. You just want to store a collection of things. Okay, the collection can be the same things, it can be different things. Like in the example here, we have a collection of fruits, bananas, mango. Like, you can go, if you're a farmer, you can be returning from the farm and you have a large basket and you harvested a number of fruits. All your fruits can be in that basket. It can be different fruits. It doesn't matter, right? So if you just want a collection that just stores things, and for your use case, it doesn't matter how those things are stored, or it doesn't matter that they are of different type, arrays are great. You want to be able to you want to do random access. You want to just dip your hands in the basket and just grab any fruits, random. If you need random access, arrays are great for that. Okay, so based on that problem, based on that situation, you can use the array data structure because the properties that it has and the capabilities that it enables allows that. And then we looked at linked lists, right? And we said linked list is like arrays, but the linked list maintains insertion order. So you care about order. So this is not just a collection of things now, but it is things where the first thing that goes in, the linked list knows that this was the first thing that was put in. This was the one that was put in next. This one is what that was put in after that. So if you care about insertion order, the order in which the things go in, then if you care about, how you get the things out, and then you care about the third critical thing is linked lists. If you grab any node or any item in the list, you can say, hey, given this node, who is the next or who is the previous? Okay. For a singly linked list, that's a list that is linked only in one direction. That's what singly linked list means. It means that if I grab one, I can say next, 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 next. I can't do previous, previous. Okay. I can do next, next. So I can only move in one direction. I can move in a single direction. That's why it's called singly linked list. Grab one node, whether that is the first node or is the middle node or whatever, I can say, is there a next? Go next. Is there a next? Go next. Is there a next? Go next. For a doubly linked list, so it's a list that is linked in two directions. It means I can go next, next, I can go previous, previous. So imagine if people are on a queue, I can just grab the guy in the middle and say who is next, and I will get that next. And I can say who is before you, and I will get that. So if you care about that sort of operation in your data, then you would use a linked list. You would not use an array because an array does not have that. An array is random access. An array is just, this is the collection of items. I know that I want item in position 0 and I just get position 0 and that's it and I'm done. Okay. But if you care about insertion order, you want to be able to go next, next or previous, previous, do like a navigation, then an array, if you use an array, you would not be able to solve that problem. Okay, so tying it back to solving problems, you will not be able to, well, let's not say you will not be able to solve it. Like, you will not have to your code will be hacky. You'll be writing hacks. Instead of an actual solution, you are cutting corners, your code will be buggy. Like you will be, it's like swimming against the tide. You'll be doing things against, what is normal and what makes sense. Okay, and then the third one we saw was stack. And the example I gave is people clearing dishes from an event. You go for an one day, like a wedding or a birthday, you are done on your table eating, and then someone comes to come clear the dishes. As they pick up the dishes, they will stack the plates on top of each other, right? And then they will carry the plates away. And then when the plates gets into the kitchen where they're going to wash them, the person who's going to wash them is going to start picking from the top, right? So a stack, we said, is a last in, first out. So the last plate that got into the collection of plates is going to be at the top. And that last plate, it was the last one in, is going to be the first one out. That's a stack. And a linked list, we said, is a first in, first out. Okay, so just breezing through some of the things we saw the last time. And then the last one we saw was tree data structure. And we said this one allows you to represent a hierarchy. I want to be able to say, this is the great-grandparents, this is the grandparents, these are the parents, these are the kids. That kind of hierarchy. Or this is the CEO, this is the CTO, this is the, I don't know, this is CEO, this is the, what's the hierarchy? I don't know, VP of engineering or something. No, CEO, CTO, VP of engineering, engineering manager, I don't know, maybe staff engineer, and then some other engineers, senior engineers. Just so you want to represent that kind of hierarchy, you can do that with a tree. Even though the linked lists might resemble something that you can use to do a tree structure, a hierarchy, it's not actually suited for that. And the reason is that for a tree, you can see that given a node, we can say we are not just able to go next. So from item 1, we can go to item 2, but we can ask item 2, are you a parent or are you a child node? Are you a parent node, which means you have children nodes? Item 1 has 2 and 3 children nodes, child nodes. But item 6 has a child node of item 10, and item 10 is a leaf node. So leaf node is like the terminal node, like in an actual mango tree. The leaves, there is nothing else after the leaves. You can have the roots, and then you have the trunk, and then from the trunk you have branches, and then from branches you have like maybe smaller branches, and then from smaller branches you terminate at the tree. So in this hierarchy, item 8, 9, 10, 11 are leaf nodes, they're the terminal nodes. But all the other items, while they are nodes, they are also parent nodes because they have children. Okay, so just a way to say there are different ways of organizing data based on what you want to do with the data. So because we want to represent an org chart, you are building a HR app, or you are building, I don't know, you are building an app for sports, and you want to be able to represent hierarchy. This person came first, and then this 2 and 3 are ties. I don't know. You can use a tree structure for that. Okay, so let's look at algorithms. And after that, we can look at, or maybe before we look at algorithms, I can pause and ask if there's any question, and then go through this stuff that I put together from the last time. Someone asked me if there was a practical example that I can share for this, for data structures, and I was going to share something. Okay, so I did share this, or I said I was going to share something, and I can share this link with you guys, Jerry, so that everyone can take a look, because there's really no time to cover everything here. But this is a very simple example of a data structure that I actually used some years back. So I don't know the level of experience that we have, but the problem was we were building an API, and the API needed to have it needs to sort by multiple fields. What's common, very common, is you can sort by a single field. So you have an API. For example, here you can see that we are saying we want to fetch products. Let's assume that it's an e-commerce platform or something. Normally, you would sort by the name of the product. Like, imagine you going to, I don't know, what example can I give? Like Shopify. I'm not saying Shopify does it this way, but just using Shopify as an example. Ideally is, or if you go to, what's the name of this popular e-commerce platforms in Nigeria? Konga or something. And you go there and you type MacBook, right? Typically, they would sort the result you get by a single field. And that single field can be, maybe they're sorting by the name of the products that are being displayed, or maybe they are sorting by the dates when that product was, made available, or they are sorting by the price. They are normally sorting by one. What's very common is that they are sorting by one dimension. So name or dates created or dates updated or price or whatever. But in this scenario, we needed to sort by multiple fields. And then it's one thing to sort by multiple fields, because you can also assume that you're sorting by multiple fields, you're sorting them in one direction. Okay, so when I say direction, I mean, is it ascending or is it descending? Are you sorting, so by, if it's price, for example, are you going from the highest price to low, or from the lowest price to high, right? So there are a number of things going on here. Not only are we sorting by different things, each of those different things have their own direction. So here now we are sorting price. We are saying go from up to low, right? Go from like the low price. How did I interpret plus again? Yeah, go from low price to high price. I want to see the lowest price first. And then the same way for rating, we are sorting by, rating has its own sort direction, and stock has its own sort direction. And so there's no limit to how many fields you can sort here. The API didn't say, you can only sort by 5 fields. So the fields can be quite a number, and then each one of them have their own sort direction. So this is the input data you are getting. A single string separated by a comma, each field has its own sort direction. And you know that ultimately when this hits the back end, we go through validation and everything, we do all that dance. Eventually, we are going to translate this into like a database, query. Let's assume that this platform is using a SQL database. You are going to do something like a SQL query that says fetch from products, fetch star, fetch all the fields from products, where they put a criteria. The where would be if the person was searching for Mac, where title is equal to Mac or something, right? And then you will now apply this sorts. Okay. And so in that scenario, you're going to now tell the database, okay, I want to sort by price, I want to sort by rating, I want to sort by stock. So one way, like I was saying, is we get this input data ultimately it ends in a database sort, or an even simpler way, simpler in terms of like implementation, not simple like is the right thing or wrong thing to do. An even simple way is that you fetch your products, right? Give me all the products that match the search criteria. The user is searching for MacBook Pro. Give me all the MacBook Pro products. When you grab all the records, that wouldn't do that anyway. And then in your code, you have the list of, I don't know, 500 or 50 or whatever records. You now sort those records in memory, applying these sort criteria. So I'm trying to describe the problem, right? And so what did I do? All I did was, very simple. Like, how can I go from a single string that is phrased like this? This is how the API request will come. How do I go from that to something that how do I represent this data in a way that my backend can use it, whether we are doing database sort or whether we are sorting records in. And so what did I do? A simple JavaScript object that represents, hey, what is the field that we are going to sort and what is the direction that we're going to sort. So each of these things here, each of them separated by comma, is going to be translated into something like this. So we are going to say that the field is price and the direction is going to be either ascending or descending, right? Very simple. And then because we have a collection of fields, right? While this represents one, we actually need to represent all of them. So we need to have an array or a set, because arrays allow duplicates. So we're going to have a collection that says, hey, these are all the ways that this API request, the data that we get from this API request needs to be sorted. This is all the ways that the user wants them to be sorted, okay? The first one is we want to sort by price, ascending. We want to sort by rating, descending. We want to sort by stock, descending. So this sort of captures how the sort operation needs to happen, and that itself is the data structure, right? So sometimes we look at data structures as one very, it can be complex, one very abstract, very, obscure thing. But it's, like we said, for the examples we give about arranging books and oranges, it's just a way to say, hey, I have this problem. I know the end goal. I know what I want to achieve. How do I represent the data in a way that I'm able to do that, effectively, right? And then once you have your data structure in place, it's not a case of, okay, is there like an algorithm that I'm going to use? Is there an inbuilt way? Is there an inbuilt algorithm that I'm going to use to do my sorts, or do I want to write my own? Or even if I'm not writing my own, do I want to use an inbuilt sorting algorithm to do the sort now that I have a representation of how the sorting should happen? Do I want to use an inbuilt algorithm, or do I want to implement an established algorithm, like, implement it and then swap it with the inbuilt one? So what I'm trying to say in essence is, problem statement is get products, sort by multiple fields. Each field can have its own, sort direction, and we represent a single sort field this way, and then we represent the collection of sorts this way. In this case, we're using an array, right? So I will share this file with you guys. There's code here. You can go through it, whatever. I'm not sure we have time to go over all of that. But what I wanted to show is that at the bottom, I put a few things to consider to improve that data structure. So for example, right now we have the data structure is an array, and you can see that each of the items inside has the field and the direction. If you look at the code, you see that there are other things. For example, we actually have a field, an additional field here called sorter, like the function that will do the actual sorting. And I think I also considered putting an ID there. But this is using an array. An array is, I'm not sure we mentioned it before, arrays as a data structure allows duplicates. And so you can see that now the price is being duplicated twice. So if you use an array as a data structure for this, yes, you can represent each of the sort instructions like this, but the collection of the instructions, if you use it as an array for your data structure, then you run the risk of having duplicates. Even if you are careful enough, this is going to happen in runtime. So you can do validation. There are a number of things you can do to prevent duplicates, but I would even prefer that you prevent duplicates at the data structure level. That is, use a data structure that even does not allow duplicates. If somebody even tries to put a duplicate, like, there will be an error. That's what I would recommend. So while using an array gets you off the ground, these are my collection of 3 ways that the user wants to sort: price, rating, stock. There's nothing stopping another engineer from making a mistake and putting price twice. And so what that means is that the sort operation is going to happen for price twice, right? And it might be nothing, it might lead to a bug, but the point is that you don't want that. So arrays allows duplicates. So maybe you might want to use like a set. A set does not allow duplicates. A set is a data structure that has a collection of things, but unlike arrays, if you put a duplicate, it will reject it. Not that it will throw an error, but as long as there's price there already, it will not take the new one that you're trying to put in. So that way you ensure that each of these sort representations inside a collection are unique. You're only sorting them once. I mean, there are also situations where you might want to sort price twice, but if that's the case, let it be clear, let it be explicit that I want to sort price twice. Okay, so that's one improvement that we can do to this very simple data structure. Okay, so that's the example I wanted to share for data structures. We can go into algorithms now. Cool. So algorithms are simply steps for solving a problem. You know, I like to start very simple. And sometimes when I simplify things like this, people feel, you know, like it's too simple. But yeah, like if you really distill it, if you really break it down, this is all that it is. It's an ordered list of steps to solve a well-defined problem, right? And so whether you are sorting, whether you are searching, whether you are doing file compression, right? There's someone gives you a large PDF file and your software needs to compress that file from, I don't know, 50 MB to 5 MB. Whether you are doing media like audio or video compression, like the algorithms is just, these are the 10 steps, these are the 15 steps, these are the 5 steps, this is the sequence of order of operations that we need to do to solve this problem and do it in an efficient way. The only other thing that algorithms have is that there is a way to measure them. So we're talking about list of steps to solve a problem, but it needs to be measurable because we want to be able to say, oh, this algorithm is better than this algorithm, right? And when we say better, we don't want that to be vague. We don't want that to be better because I think it's better, or better because I wrote it. You know, we want it to be clear, opinionated, deterministic, it is repeatable, right? So algorithms have that added feature of, it's like a scientific method where, you know, they say something is not a formula until it is well defined and it is repeatable. You can pass in the same data and run the formula to give you the same result every time. So that's like what an algorithm is. So like clear steps to cook jollof rice. There are many ways to cook jollof rice. There's a way my wife does jollof rice. And if she does it that way, following that recipe, it comes out the same way. The taste and the smell comes out the same way no matter what. Whether she's cooking it in my house or she goes to a friend's house, or like we're spending the weekend and she cooks it there. Like it doesn't matter what pot she, well, it doesn't matter. It doesn't matter so much what gas cooker she's using or what pot she's using or whatever, unless the algorithm is one, unless the steps for this particular rice effect you want to get requires a particular kind of pot. Okay, if the pot is now part of the inputs. But if it is not, if it is just pure ingredients, then as long as we know the amount of ingredients, the order in which you put them, you know, the quantity in which you put them, the amount of heat and the timing, like once you know all those things and you put them, these are the instructions and these are the steps, then that's an algorithm, right? So whether it's cooking rice, whether it's getting a guy or a babe, you know, whether it's like the last example there, like you are building a portal for a university that is really large. Some public universities in Nigeria are really large, and their data even grows exponentially over the years. So like take a University of Benin where I finished from, like if you were to search for Like when I was working as webmaster at University of Benin, like it was very easy for people to send us a mail and say, hey, I graduated from Uniben in 1970. I'm just making these dates up, but like 1973, like even probably before I was born, right? I graduated. I am now in the UK. I'm about to retire. There's something that the government wants me to verify, and now they're asking me to go do some verification in my, from where I claimed I graduated, and they'll give you their MAT number. So imagine you are building the portal for that kind of school, and now you need to search your database that the data has grown over 10, 15, 20, 40 years. You now need to do that search, right? Of course, there are things that can help you narrow down the search. Like if this person tells you I graduated in a certain year, or like I got into school this year and I graduated this year. If they provide all that information, yes, it might help your search if your app was built that way. But sometimes they might even have forgotten all that information. Like maybe all they know is their eng number, their matric number, or maybe they even know just a portion of their matric number. And so now you need to search this large database of student records spanning, I don't know, hundreds of thousands of records or even millions of records. Okay. And so the point is, you want to be able to do that, do it effectively, correctly, get the correct data. You want to get the correct data and the correct results, but you want to do that effectively. You don't want, because somebody is doing that search, your entire backend shuts down, the entire backend slows down. And then people who are doing other things like course registration or maybe even taking courses online can no longer do that. So an algorithm is just, I want to perform this action, but these are the clear deterministic way that I am going to be able to do it, right? Do it correctly, and do it repeatedly. Good. So how do we build algorithms? I think I've covered this already. State the inputs. Like, what are we getting, right? Like in the jollof rice case, what are the inputs? If it's fried rice, what are the inputs? So state the inputs. State the conditions. What type of data do you need? Does the data need to be sorted? For example, if you want to use binary search, we'll look at binary search soon. It's more like, I was going to say it's more effective. Like, is it even more effective? Like, if the data is not sorted, you can't do binary search. But the data has to be sorted. The data has to be sorted. That's why in binary search, as we were saying last week, when they give you a large collection, you can say, oh, instead of combing through all the items in the collection, because it is sorted, you can just say, hey, I will land in the middle. And when you land in the middle, you know that if that middle that you land in is not what you are looking for, based on some conditions, you can know that, oh, it means that everything on the right is already not going to be what I'm looking for. So you can eliminate them, right? So that's landing in the middle and eliminating the left or the right is made possible because the data for binary search is already sorted. So if the data is not sorted, then everything falls apart. So you need to state your inputs, state the conditions, and then what are the steps? So given these inputs and given these conditions of the inputs, take this step 1, 2, step 1, step 3, step 4, take these steps in this order. Of course, these instructions for the step might also include conditions like branch here or branch here, things like that. But once you take all those steps, given the input, given the conditions of the inputs, following the steps, you will always arrive at the output, right? And then the final thing to emphasize is there is a way to communicate about algorithms. Because if you ask me to build a search algorithm and you ask another engineer to build a search algorithm, we can both come back and say, hey, we found the same results. Okay, but how do we communicate how our algorithm found the results? How do we communicate the performance of the algorithm? Which one is faster, which one is slower? Okay. And big O notation is what is used to do that. Because we have limited time, I don't have to go into all the details. But big O notation is just a way, is the language of communicating algorithms. So if engineer A builds the algorithm and writes, like communicates the performance, the structure and the performance in big O notation and shows it to me, I will understand what it is. And if engineer B does the same, not only will I understand the algorithms that they've written, because they both use big O notation, I'll be able to say, oh, engineer A's algorithm is better or is faster for so and so and so reason than engineer B's condition, than engineer B's algorithm, sorry. right? For example, we can use big O notation to say, oh, binary search is better, and better is even vague. You can say binary search is faster. Even faster, you can further distill it down. You can say binary search is faster by this magnitude than linear search, right? Because we can use big O. Big O notation enables us to sort of capture all of that detail. So big O notation is just a way to represent algorithms in a way that they can be communicated. It's like the language, is the lingua franca of algorithms. And this is an example of big O notation. Okay, not something we can cover in this class, like all the details, but you can see on the left we have time. So going from the bottom to the up is this. So the algorithm is running now, starting from, if you can see my cursor, starting from here, the algorithm is running. This is time. This is how long it takes for the algorithm to run. And this is input size. Okay. So all these things you are seeing here are the various ratings, the various ways or notations that an algorithm can be rated or can be scored. Okay. It's like the scorecard of an algorithm, right? And your algorithm represented in big O notation, it can be given a scorecard that will fall into one of these categories. You know, O of n, O of log n, or whatever. Like this is mathematical notation anyway. But the point I'm trying to make is what this graph is trying to say is that as your data is improving, as your data is increasing, you've done your data structure, you've written your algorithm. When I call it algorithm with five items, how does it perform? When I call it with 1,000 items, how does it perform? When I call it with 1,000,000 items, how does it perform? When I call it with 100 million items, how does it perform? Or if you have a database, right? Databases obviously use algorithms. That's how they perform queries, and they perform queries really fast. So it's like saying, how does your database or your API request, how does it perform? How does your database perform when there are only 5 records? So if you're building an e-commerce shop and you use a database, databases have inbuilt algorithm. How does your database perform when there are only 100 products in your database, right? Versus when there are 1,000,000 records, right? And so this is potentially part of the reason. I'm not saying it's the only reason. There are many reasons, right? It's potentially part of the reason why you hear that some sites crashed on Black Friday. Black Friday, where many people are doing promotions. You know, they are saying 50% off, or they are doing what's this thing called? They are doing scavenger hunt on their websites. They are saying, oh, there is a 75-inch TV, 75-inch latest Samsung Smart TV on the website, but it's not in the TVs section. So if you can go to the website and go and scavenge, and if you can find it, you can get it for free. And so now there are 1,000,000 people on your websites trying to click through all your random pages to find that TV because you want to get it for free. And then you hear that the site shut down, right? Or you hear things like, oh, people are writing jam, which has never made sense. I mean, people are writing jam, and then for some reason the jam, or people are trying to register for jam, and for some reason the jam website shuts down, right? There are many things that can cause it, but one of it is now that there is a huge data, the input size for your algorithm has exponentially grown. How does your algorithm perform? So the ones that are green at the bottom, the O of 1 and O of log n, means that no matter how large your input size is, even as the input size is growing, the impact on the performance of the algorithm does not really change, right? An example of that, let's go back. Remember we said arrays are random access, right? And so getting an item from an array does not change whether the array has 3 items or whether the array has 1,000,000 items. So let me say that again. You have an array that has 1,000,000 items. Remember that we said arrays are random access. So what it means is that this array here, if I want to get the item, if I want to get the number 10, the number 10 is in position 2. As long as I know that it's in position 2, I'll just say, hey, array, give me what is in position 2. I go there, I grab what's in position 2, I get my 10, and I go away. Like that's it, right? So whether this array has 50 items or whether it has 1,000,000 items, it does not matter. as long as I know the position of the item, I can just go there and I can randomly access it, right? And so using that as a simple analogy, we can say that random access in an array is O of 1. O of 1 means, the 1 means it is constant time. So the time complexity of that operation of grabbing that 10 from the array is constant. It's constant. Whether the array has 5 items or whether it has 1 million items or whether it has 1 billion items, if you can fit that 1 billion items in memory, yes, all it takes to grab a single item, it does not change whether the array is small or whether the array is large, right? So that's how you think about, time complexity and all of that for algorithms. So I'm trying to explain this whole big O notation. So what O of 1 means is the time complexity is constant, irrespective of the input size, right? Whether the input size is large, it does not really matter. Like, we don't need to perform more computations or less computations. We don't need to perform more computations over time, right? Irrespective of the size of the data, because O of 1 means constant time. The time it takes to grab item, the time it takes to grab item 10 is constant, irrespective of the size of the array. The time it takes to grab item 15 is constant. So that's O of 1. So if you build an algorithm, I say, hey, engineer A and engineer B, go write this algorithm. We need to, in the example I gave, we need to sort products by price, rating, and stock. Sort them in this whatever, ascending or descending or whatever, and they both go and do their jobs, and they bring it back. If they represent the algorithm for doing that sort with big O notation, I'll be able to tell that, oh, okay, engineer A's own is constant time. Engineer B's own is, I don't know, maybe this O of n, what my cursor is. And by that, I can already tell that engineer A's own, this one here, is way better, because it means that whether we are sorting 50 products, whether we are sorting 1 million products, the algorithm performs the same way, right? So I'll just explain one more. So O of n is I guess is the next one to explain. And you can also see that there are sort of a legend here. So green means good, yellow means average. So if your algorithm falls in this O of n or O of n log n, it's average, it's okay, not terrible, it's not really bad, it's not the best, but it's not really bad as well. But if it falls under here, O of n squared, then it is bad. You need to do something to improve it. So I've explained O of 1, which means constant time. So we've looked at one good algorithm from the perspective of big O notation. But let's look at one average algorithm, which is O of n. O of n means that the performance of the algorithm is, how do you say this? Performance of the algorithm is there's a mathematical term which I can't remember now. If you remember from a math, when they say something is proportional or inversely proportional or perpendicular, it's proportional. I mean, let's use proportional. Okay, so the input size, affects the performance of the algorithm, in a proportional ratio. So what that means is that as the input size grows, by the rate at which the input size is growing, that is the same rate at which the performance is degrading. So in that case, if the algorithm that one of the engineers implemented is O of n, it means that if you are sorting items that are like 100 items, and it's performing, let's say it's taking, 2 seconds to do the sorts. By the time you increase, let's say you 10x that 100, right? So you go from 100 items to 1,000 items. That ratio of change, which is 10x, that is the equivalent of ratio of degradation, performance degradation that you're going to get. And so because the algorithm now needs to comb through times 10 data, it performs equivalently, roughly 10 times slower. So that's O of n. So n represents the number of input here. So as the input size or input complexity grows, it is by that measure that the performance decreases. And so those algorithms, they are okay when the data is small. But if the data is large, it becomes a no-no, because by the measure of the largeness of the data, the algorithm will perform really slow, and probably even at a point it will halt, right? And so linear search falls under here. Okay. I think binary search is O of log n. Binary search is O of log n. Linear search is O of n. So what that means is that in the example of linear search, which we can see, let me just fast forward. Linear search, I think it was here. Really? I can't find where linear search is. Just give me a second. Yeah, this is linear search. So linear search, we are looking for 22. This collection could be large. We start from the beginning. We say, is this 22? No, we go next. Is this 22? No, we go next. So we're just saying, is this it? We just keep going until we find 22. If there's no 22, then we would have come through the entire data. If there were 1 billion records, we would have come through. It's like somebody's going to your database, like the example I gave of that matric number. The person gives you the matric number. If I'm using linear search to search my database, it means I'll be combing through the entire Univen database you get to find that matric number. What if the person gave me the wrong matric number? So I would have come through, I don't know, whatever the amount of data we have for that student the table, I would have come through everything just to find out at the end that, oh, it doesn't even exist. So linear search, you are going step by step like that. And so linear search falls under this O of n, because if the collection of data is large, you are going to potentially do all of those operations to get to the end, to even see that it is not there, or to find that the thing is at the end. But if the data is small, right, then I mean it's not really too much of a problem. If you have only like 50 items to sort or to find something from, it doesn't really matter that much. It doesn't matter that we are going we are looking at each of the items one after the other. If the data is small. If the data is large, then this O of n, like in linear search, is going to blow up in your face. Okay, and then let's look at O of n squared. O of n squared is the performance of the algorithm degrades by the square of the input size. It can be bad. Okay. So what it means is that if the input size is 2, what is the square of 2? The square of 2 is 4, right? So it is by that measure that the performance is going to degrade. In the O of n, the performance is degrading by the ratio of change, by how much the data is changing. If the data is changing by 1x, performance degrades by 1x. If the data changes by 2x, performance degrades by 2x. That's O of n. If the data changes by 10x, performance degrades by 10x roughly. Then O of n squared, if the data increases by 10x, performance degrades by 100, because the square of 10 is 100. So the impact of very little increase in data, performance of the algorithm, will be it can be very, very bad. So when you're dealing with very small data, like just 2 records, or let's say just 10 records, the square of 10 is 100. Okay, I mean, yeah, the performance it's still n squared, it's still bad, but you don't feel it too much. But when the record is now 1 million, right, then the square of 1 million is what? You can do that math for me. Is that 100 million? That's by how much the performance of the algorithm is going to degrade. So you want to try as much as possible to avoid this. Like sometimes you can't, because computer science and software engineering, everything is trade-off. Everything is, I'm trying to solve this problem using the resources I have, using the constraints I have. So sometimes you might be constrained. You might not be able to do better than this, or maybe you want to push this thing out of the door quickly, right? So, I mean, there are situations where you might not have a choice and you might need to go with this. But the point is, the knowledge of data structuration algorithms makes you know that this should not be a long-term solution. It makes you know that this code you have written here is just a matter of time before it's going to cause serious problems. But people that don't have that knowledge, they are going to be oblivious. And what oblivious means is they don't know. They just write the code, oh, it's working, and they're happy, right? Or maybe the problem is you are a senior software engineer, or you're a tech lead like me, or you're whatever, I don't know, and somebody tells you, your boss tells you that, oh, whenever we perform this operation, it slows down. Something is just wrong in the back end. And then because you know data structures and algorithms, you can go and look at the code, and there are patterns. As soon as I see a pattern that can cause this, like I already know. And one classic pattern, which I'll just put out now, wrap up this slide, is when you do nested loops. Anytime you're doing a nested loop, that's a prime candidate for n squared, sorry. If you are doing nested loop, let's say you are looping through, and a classic example would be in your code, you are saying, give me all the products in the database, and then you get all the products. And then for each of those products, you are now going back to the database again to go and say, give me all the orders for this product. So within a loop, you grab an item, and then for that item, you enter another loop again. Especially if that other loop, that nested loop that you've entered, is iterating by the number of times that the parent loop is iterating, right? Then, you know, that's a prime candidate for n squared, O of n squared. Might not be a problem if the data is small, but as soon as the data begins to grow, even if the growth of the data is little, because the performance degrades by n squared, you will see the impact at some point. So all of this is just to say big O notation is a way to represent algorithms, and all of these things represent different performance like bands of an algorithm based on, you know, input size and time. Whether it's time complexity or whether it's space complexity. So I'll wrap up by saying time complexity, which is what we have talked about most times here, like so far here with this big notation. Time complexity is you are evaluating how the performance of what is the performance of the algorithm in terms of time. Is the time to do a computation improving on the degrading as input increases. But space complexity is a slightly different one. Space complexity is you are saying this algorithm is it a greedy algorithm? So space complexity is how much space, how much memory or how much disk space, how much files is it, like how much of actual memory or disk space is your algorithm occupying? Okay. And these two things, time complexity and space complexity, sometimes you might not be able to achieve them, like do very well in them. So you need to trade off, like what matters the most. Sometimes there is a conflict between, do I optimize for CPU? Do I optimize for memory? You might not be able to optimize for both of them at the same time. So the same thing applies for to algorithms, where sometimes it's difficult to optimize for both time complexity and space complexity at the same time. I need to trade off and say, okay, I want to focus on making sure that this algorithm is really fast, even though I'm going to put more items in memory. But I think it's fine because I know that, once the algorithm is done, the objects in memory are going to be orphaned. And because of that, they're going to be garbage collected. So you can see how I'm phrasing it. So if I present that case to like my CTO or like a principal engineer, they can understand, okay, that's a nice trade-off. Algorithm is really fast. The user is going to get the results on time, whether they are searching or sorting. Whatever data we are pouring into memory or disk space, there's going to be either a manual cleanup process or the system is going to clean up by itself automatically. So that might sound like a reasonable trade-off for that scenario. In another scenario, it might not. So algorithms, again, is just, I have this problem, I know the inputs, I know the conditions that the inputs needs to be. These are the steps this is like the formula or the recipe. And when if you give me those inputs with the right conditions and follow that recipe, you are going to get this output, right? And I don't know if we have time to look at, so there are a number of algorithms that I mentioned here. There's sliding window, you guys must have heard of it. What can I do now? Maybe we should talk about 2 pointers. I think this is a simple algorithm we can talk about. So 2 pointers, this one is, and then we can wrap up with this. So 2 pointers is an algorithm for, so remember the case where we said for linear search, where is it? Linear search. Yeah, for linear search, we are searching for 22, but we are starting from the left. We are checking 15, 9, 35. We're just going like that until we find 22. 22 here is in the middle. It could have been on the end. This list could have been large, whatever. You are saying, I'm looking for 22. I have a list of data. I'm looking for 22, but I have one operation. I have one computation. Let's put it that way. One computation or one operation that is doing the looking, that is doing the searching, that is doing the lookup. Okay. And so we are calling that one single operation that is doing that lookup. We're calling it the single pointer. Okay. Now, there's an algorithm, very simple, but very effective, that is called two pointers, right? And it's just, all it's just saying is, well, you can improve this search task by doing the lookup in two places, okay? Remember I said the pointer is just the lookup, is the operation, is what's doing this comparison, what's doing this is 1522, is 922. That operation, instead of doing it one at a time, can we double it? Can we double it? And so if we can double it, it means that while we are searching for 22 from the left, we are also searching for 22 from the right. The benefit of that is if 22 were to be in any of the edges of that data, we will quickly find 22. So imagine a situation where 22 was at 17, where 22 is at where 17 is right now, right? It means that if we're using only the pointer on the left, we would do many operations to get all the way to 17 to find it. Like we would have scanned from the beginning all the way to the end, almost the end, before we know that, oh, let's say we're looking for 17, okay? We would have gone from 0, 1, 2, all the way to here before we find 17. But if we use two pointer, this guy, the second pointer, will only move once. I need to find 17. And once we find 17, we end the entire operation. So two pointers is just a very simple way of saying, I have a collection of things. I want to search for something, but instead of doing it with one operation that goes from one end, I'm going to do it with yet another operation so that I can double the chance of me finding it quickly. Two pointers might not really help if the item you're looking for is in the middle anyway, but it's just a slight improvement over linear search. So very simple. Like this is something that in your JavaScript code today, you can actually start doing. You can actually say, if I have an array of items, if the array of items, if the length is more than 500, right? Instead of using a single pointer, I'm going to use two pointers. I'm going to use two pointers. I'm going to search both from the left and from the right, and I'm going to, hopefully get to find my item quickly, right? Yeah. So I really don't have much time. I think I've spent more than an hour, but I can pause here and take questions. And then I'm happy to share this slide and the GitHub. This repo, there's actually no code in there right now. It's just a simple README, but you can read through it and then I can take questions maybe later. But yeah, so the summary of it is, as an engineer, you're constantly going from problem to solution. Data structures and algorithms is a powerful tool that enables you, sometimes more than other tools, to be able to do your job of going from vague problem to clear, measurable, deterministic, repeatable solution from time to time, right? It also builds your mental ability to do pattern matching. So like, remember I said, whenever I see a nested loop, I can already pattern match. I can already tell you that, oh, this nested loop, I mean, it doesn't mean that every time I see a nested loop that that is likely going to be what's it called, O of n squared, but there's a high tendency that there's a more than 85% chance that that nested loop is going to be that, especially if the data is going to be growing. The data is going to change. If the data is constant or hardly changes, then maybe. But if the data is going to be changing, like you're pulling records from the DB, the records from the DB can grow as more records get put into the DB as the business grows. So if you're doing that kind of thing with a nested loop, I can already see that just by looking at the code, I can already tell because of this knowledge that this is going to blow up, right? So you can say that knowledge alone, and it can be the reason why I can quickly fix a bug and why maybe another engineer, is not able to fix the bug. Maybe the engineer, you need to like reproduce the bug Of course, you need to reproduce bug before you can fix it. But sorry, when I say reproduce, I mean the bug is happening because the data that we are dealing with at that point in time is large, or the rate of change of growth is large. So we are seeing that bug. But I know that, and I can tell that just by looking at the code, even without paying too much attention to the data. If another engineer might not know that because they don't know data structures and algorithms, and they don't know what this O of n squared means. Okay, so that just gives you a good idea of how this knowledge helps you to be effective, whether it's building solutions from scratch, whether it's refactoring and improving solutions, or whether it's debugging, or whether it's communicating to other engineers. And with that, we call it a wrap for today. Maybe I can take one or two questions.
So I'm like curious, if we were to sort in range, like for price and rating, that their numbers are like numerical values, like if we were to sort range of values, say price should be between this and this value, how would we possibly, or why I just want to like, can you just give like a brief high level, of how you would approach that kind of scenario? So we need to represent them, not just like ascending order or descending. We need to get like the values in range of X and Y. How would we possibly modify this data structure?
Yeah, so the way I would do that is, first of all, remember that the input is coming from here. Where is that? At the top. So it's coming from here. So it means that there has to be a way for us to capture that range in this place. So the way we say price, there has to be a way to put the range in here. So maybe, how can I type now? So maybe instead of plus price, it would be, maybe the API would accept plus price, colon, I don't know, 20 to 100, right? Comma, and minus something else. You get plus stock, minus stock, something. We need to, so the first thing is that we need to capture that data. We need to capture, remember I said algorithms, it also applies to data structure, like your input needs to be clear. So you need to capture that. And then, of course, we need to pass this. So right now we are just saying we split by comma, and then we get the field and the direction. But now we're going to split by comma. We will get the field, which is price, we'll get the direction, which is plus, and then we'll get the range. So the first thing I'm saying is, right, you need to get that, put that in your data. Then once you've done that, we need to be able to represent that range in, am I going too far? I think I am. Yeah, we need to be able to represent that range here. So if you see this order of operations here, we go from price, comma, rating, comma, stock. We use the split operation, and then we split it into an array of price, and all of that. And then from there, we go into this, the final data structure. So we need to improve this process such that that colon, whatever that colon, price range that's going to be after here, right? That transformation needs to happen so that these objects here represent that range. So the way we are saying field is price, direction, ascending, we might need to put something else here that represents what that range is. So the way I would think about it is I would say, come on, you can't copy. I would say field is, I don't know, plus price. No, field is price, sorry. Price, and direction is whatever ASC. And then I can say value. I don't know if I want to call it value, but something. And so that thing can be a single value or a range value. Do you understand what I'm saying? So we can say value is 2, and I think we had compare there. The compare is a function. So that's what we used to do our comparison. So our default scenario is value is optional. We don't care about it. Or if it is there, it's a single value or it's a range of values. So something like 2 to 10, we can represent it that way. Right? Anyhow you want to represent value, you want to represent the range. So once you've captured this, that's all. You've represented that information in your data structure. So what you now need to do is make sure that your compare function can deal with this range value. Because right now, our compare function, This is how it's dealing with single values. It expects that when we get our collection of records that we want to sort, there's going to be a price field in there, and the price field, the value for it is a single value, right? So we need to modify our compare function to make sure that because this value here is phrased or formatted or represented as a range, then our compare function is smart enough to know that, oh, we are doing a range comparison here. Yeah, and then it will sort based on that. Yeah. So that's how I represent my data structure, like without doing like serious analysis. Or of course, if we spend some time, we can improve it and make it better. But off the top of my head, that will be like my starting point. I can even do a POC, proof of concept, with that, and improve it and go from there. Okay, one more question.
I wanted to ask about the two-point algorithm. I just wanted to ask, could we have endpoint algorithms too?
I've seen it, but it gets complex as you increase pointers. So just so you understand, the two-pointer concept is just because arrays are not necessarily all stored like this. This is a visual representation, but this visual representation makes a lot of sense. And so the two-pointer concept is because we have two ends, right? So you can see that we can start computing from here, we can start computing from here. And so if you're asking whether we can have multiple pointers, I mean, why not? I don't see any reason why we cannot have 4 pointers or 3 pointers. But let's say 4. So one is starting from here, one is starting from here, and then 2 are starting from the middle. So the middle one, so while one is going from left to right, one of the middle one is going from middle to left, right? Then another one is going from middle to right. So just you can do that, but the complexity of that algorithm, I feel, will not warrant it. It's not deserving of the complexity that your code will have to manage those 4 pointers. Will not necessarily make sense, because remember again that even though you have multiple pointers, you are doing your search linearly. It's still linear. It's just that you are doing more operations. Just that there are more operations doing the linear search for you at the same time. That's what it does. And so the same result you are going to get, when I say result, I mean in terms of like time complexity for that algorithm, you are probably just better off doing binary search. So that's how I phrase it. So the answer to answer your question, can it be done in code? Yes. Should you do it? Does it make sense to do it? Probably not.
Okay, thank you.
Yeah. Cool. So I hope we've learned a thing or two. Please let me know, react if you like, because the data structure and algorithms tend to be a very complex topic, and people struggle a lot. So I hope this has been valuable. I have this very nice concept. I stole this image from the internet. I love this idea called death by 1,000 cuts. Okay, so it's like, okay, let's use this example. Recently, there's been stories of home invasion. So people in Canada, random people breaking into people's homes and invading and maybe trying to rob or whatever. So let's assume I want to protect myself. Instead of struggling to go and get a license to get a gun or something and learn how to shoot, God, I've not carried a gun, learn how to shoot, learn to keep it safely in my house so that my kids that are very curious will not go and carry. Like, there's so much involved in trying to get a gun and keep it and use it just so that you can protect yourself from intruders that have been breaking into people's homes in Canada recently. Rather than doing that, why not use your regular bread knife or your regular knife or using cutting meat or cutting vegetable that is readily available in your kitchen, right? That there's nothing so special about it. Your kids have seen it over 1 million times. They won't go and carry it and play with it. If they see a gun, they will go and carry it and play with it, okay? Why not use that gun and then disarm your intruder and eliminate them, by 1,000 cuts? So this analogy here is there are a good number of computer science, data structure, algorithm, performance, infrastructure problems that you can solve, that when you look at the solution on itself in its own, it looks very small. But when you do that in many places across your code base, then the impact becomes huge. Like that 2-pointer one, it looks very, very small, very, very simple, you know. But if you use 2-pointer in your code base, your backend code base, you're you're iterating through records, and instead of using a single pointer, even though the records are like 100, that few 2 or 3 milliseconds improvement that you get here and here and here and here across your entire backend stack, like when an API call comes in, from the validation to calling your services, to hitting the database, to coming back on the database, like that entire round trip. If you use 2-pointer in like all that layers, you'll be surprised that 2-pointer on its own doesn't really do much because the improvement is negligible. If you use it across that call stack or that call round trip, you might look at your logs and see that, oh, but just by doing that, you've shaved off 20 milliseconds from your API response, right? And you'll be surprised what removing 20 milliseconds or a few milliseconds from an API response can be. It can be the reason why somebody gets promoted from intermediate engineer to senior engineer. You'll be surprised, right? If they're working on a large code base and they do some of these small things, but they do it in a good number of places, in the critical path for executing those API calls or critical path for their database, right? You will see the improvement. So death by 1,000 cuts is you're doing small things on their own. They are small, but put together, they can have a huge impact. So I'm wrapping up by saying, take the next step. Don't be like those people who see data structures and algorithms as one very complex, one very abstract thing. It can be, but it doesn't have to be. Like if you approach it with simplicity and start small, start with the simple things, understand arrays, understand maps, understand, random access, understand simple algorithms like 2-pointers, understand when something is O of 1 versus when something is O of n versus when something is O of n squared. And for example, now you know that as much as possible, avoid nested loops. If you can avoid it, avoid it. If you have to do it, make sure that you are doing it and the data is not large, data is not growing. In fact, if I ever do nested loops, I'll put a comment in the code and say, hey, to do or fix me or something, and say, let's revisit this if the data is growing or something, right? So those little things here and there is the equivalent of like death by 1,000 cuts. Like, you remember we started by saying there's a battle that engineers are fighting and you need to be battle ready. So this is you being battle ready, facing your problems and being ready to pick out your problems by 1,000 cuts, by these little small things here and there that you know. And that's all from me today.
Thank you so much. Thank you so much. I'll get the slides from you and then share with everyone. Really grateful for the time, Charles. Really, really grateful. Thank you.